Okay, thank you, Bill. That was a great introduction. Let's start with the dogs. I have a 12-year-old half Cavalier Spaniel, half Cocker Spaniel, and I have a 5-year-old half Cavalier Spaniel, half Poodle. And one of them is very calm, and the other one is very energetic. I leave it as an exercise for the listener to predict which is which. As Bill said, my name is Steven. You can find me online basically everywhere as Fractaled Mind. I have followed much of the advice of Joshua to be an open source contributor. I've contributed to Rails and the SQLite 3 Ruby gem and maintain another handful of gems myself. If you happen to have heard of me or seen my face or seen Fractaled Mind somewhere, it's very likely because of the work I have done and the incessant talking I have done about making Rails the best framework in the world to work with SQLite. And I had the opportunity earlier this year to work on a video course to sort of lay out everything that I know on how to take advantage of the leverage that Rails and SQLite together provide to build high-quality applications quickly and simply and cheaply. For those of you who might be interested, you can give me money. I'm open to it. It's not a requirement, but it's an option. There's a QR code. There's a link. Feel free to check it out. But today, I'm not going to talk about SQLite at all. I'm actually going to talk about one of my other passions, which is background jobs. And there's a lot to say about background jobs, and I have talked about background jobs from a number of different angles. Today, though, I want to focus specifically on how do we test background jobs. And I want to start with what is perhaps a bit of a spicy take, but I believe it to be true. If you want to test a background job, you need to test its retries. And if you're not, you have an anemic test. And the reason why is pretty straightforward. The thing that makes background jobs interesting, the thing that makes them different from any of the other Ruby that you execute in your programs is that they can and will retry. So the situation that is distinctive, the situation that is interesting about the background job is the situation in which it retries. And yet, I would hazard a guess that nobody here has a single test of a background job that tests it when it retries. And the reason why is that it's a pain in the ass. That's why we don't do it. It's hard to do. And so what I want to talk through today is a tool that I have made to make it easy for us to test our background jobs well, to test our background jobs when they retry. So the name of that gem is Chaotic Job, and I want to walk through a number of its features, how they're implemented, and how you can use them to write better tests. So let's start with the simple case. I want to have a job retry, and I want to test it in my CI. So let's imagine an incredibly stupid job. I've written one. This is a gift of mine, actually. I'm very good at writing stupid jobs. So this is a job that's going to fail the first time we run it and succeed the second time we run it. All right, so how might we test this? I imagine that you, like me, have read the Rails guides. Thank you, Ridwana. And you're like, I know how to test this job. I will wrap my call to perform later in a performing queued jobs block. Then I'll write my assertions. Easy peasy, done. Unfortunately for you, that is a bad idea. And the reason why can be observed if we pay attention to our logs. when we're running our tests. Let's see what the logs, I'm going to simplify them, but I'm going to keep the order. All right, let's see what our logs would look like. We're going to start performing our job, execution number 1. The next log line we're going to see is that we're performing our job, execution number 2, immediately. We have performed the job, execution number 2. Okay, cool. Now we have enqueued the job, execution number 2. The next thing we see is that we're retrying the job, execution number 1. This is bizarre. Now we've performed the job, execution number 1. And now at the end, we've enqueued the job for the first time. This is nonsensical. This is not anything at all what you would see in production. There are a number of odd things here, but I want to focus in on the fact that what we see here is that immediately as we start performing the job the first time, we start performing the job the second time. We perform the retry inside of the performance of the first attempt. And we see that we have the enqueue event at the very end. And the reason why is that this perform enqueued jobs helper, it doesn't perform jobs that are enqueued. It overwrites the enqueue method for active job to just call perform now immediately. It's completely different behavior than what you're going to see in production. And I don't know about you, but for me, I want my tests to be fast, to be deterministic, but I would like them to match behavior in production. Otherwise, they're a little bit useless, and even worse, they're liars, and they get in my way. So how can we test retries without having nonsense? This is what we want. We want to enqueue the job, start performing the job, enqueue the retry, and then start retrying it. This is what production will do. This is what we want our tests to do. How do we make our tests do that? Well, luckily, we can get there by using some different tools that the active job testing helpers provide us. We can call flush enqueued jobs until our enqueued jobs array is empty. This is actually going to enqueue and dequeue jobs in waves, much the same way that our workers would in production. And we're going to see logs that make sense. Hooray! But what if we have a slightly more complicated job? Let's imagine a job that fails the first time still, succeeds the second time. But inside of this job, we're going to do something a little bit more. We're going to enqueue another job in the future. Probably not all of our jobs are doing this, but probably some of our jobs are. I know that I have at least one job in all of my applications that starts to orchestrate a sort of collection of operations. So, in this case, we're in trouble. This isn't going to work. Let's go back to our logs and see what's going to be the case, what we want to be the case. What we're going to see here is that our first job gets enqueued. We start performing it. We then enqueue our scheduled job. It's enqueued now. So F1 here is future job. J2 is our retry. This is the second execution of our original job under test. We see that we're retrying it. Okay. Now we've performed it. Now we're performing the scheduled job in the future. And now we say we have performed the future job, our scheduled job. And at the very end, performing our retry. Okay, and now it's done. This doesn't immediately strike us as ridiculous. There's more logic here, but we do have a problem. In our tests, we have performed our future job before we have performed our retry. And this is not what would happen in production. Because in production, I have scheduled that job to occur a minute from now, and our retries are going to happen as soon as possible. What we want in our tests and what we will see in production is that we perform our retry and then we perform our future job. And what we want ideally in this case, right, for our tests to run fast is we want to collapse all of our time. I don't want to sit around for a minute and wait for the job to get enqueued and dequeued. I want it to happen instantaneously, but I still want the order of operations to be correct. Right? This is the ideal scenario for tests. Run as fast as possible, but correctly. How do we make that work? Well, if we could take our enqueued jobs array, sort it by when the job is scheduled to occur, and then take that sorted array of jobs and tell active job, all right, flush this. We could do this in our until loop, and things would work. But unfortunately, active jobs testing helpers don't provide us with this generic flush method. This doesn't exist. And this is the core pain point that led to the creation of chaotic jobs. And so the first feature that I want to talk about are the perform helpers. The perform helpers are going to take these patterns and just make them available to you, right? So perform all jobs is going to take our enqueued jobs, sort them by when they're scheduled, and flush them in waves, such that we get behavior that matches production. Now, sometimes when we are orchestrating jobs, we might need a little bit more control over which jobs we perform when, so where we want to put our assertions. So there are a couple of other helpers here. We can perform all jobs that are scheduled to occur before some timestamp or duration, after. There's a little bit of fuzzy matching there to make things a bit cleaner, so you don't get like these off by 1 millisecond annoyances. And this allows you to I want to perform this batch of jobs, do some assertions, then perform the next batch of jobs, do some assertions, so forth and so on. But altogether, these three helpers are going to allow you to test your jobs with retries in a way that collapses all time. We're not going to wait around for anything. You can set something to occur 1 week in the future. That's fine. I'll still run it immediately in test. But we're going to have the correct order of operations. Super useful. I have started the process of trying to figure out how to update the active job testing helpers to fix these problems. Unfortunately, the problems are very, very, very deep in how they have architected those testing helpers. So it's going to be a whole ordeal to get that fixed. But maybe my man Joshua can help me. This is how you test jobs with retries. Now, I have 60 more slides, so what the hell else are we going to talk about? Don't worry, lots of stuff. Failure scenarios. Failure scenarios. How do I make a job retry? You're probably not writing jobs that say, if executions equals 1, raise, right? We have jobs that we expect to just run normally, but we want to test them in scenarios where they happen to fail. How do we make that easy? Let's take this job. Simple job. It does something else, and then finally it does the last thing. Okay. Let's imagine we wanted to test a scenario where there was an error right here. After we do something else, an error occurs. How do we test that? One thing we could do, we could write our jobs to make them more testable. Here I'm using a classed instance variable to keep track of whether or not I have already forced it to error, so that I only force it to error once. And I wrap everything up, make the method have this switch in it, and I raise or I don't raise depending. Now I could just tell it to perform later, perform all jobs. I'd get the behavior I wanted. But of course, this is terrible. If we had to put all this boilerplate in every step of every job we did, it's natural that we would never do it. I would never do it. I wouldn't expect you to do it. We need a way to have this behavior without having to make our jobs horrific. And that's the next feature. We can do something like this. This is the first core concept that chaotic job provides. It's the concept of a glitch. So I'm going to break this down and really get into what a glitch is so that we all feel like we understand what the hell is going on, because I understand you're not likely to actually use a tool unless you understand what it's doing and how it's working. So the main thing I want to focus in on is like, what is a glitch? How does it work? And how does it make our lives a bit easier? So we've got this line of code here, right? We're going to create a glitch. We're going to say glitch before the call to job do more things. And when we glitch, we want to raise a retriable error, okay? What's going on here? So this helper method is a shortcut for this call to the chaotic job glitch class. The chaotic job glitch class has these class methods, which are just shortcuts for initializing different types of glitches. So we see our initialize here, like we have a particular key, then we have our event, args, return value, kwargs, and a block. We just set all that up, okay? Now, when we call glitch.inject and we pass it a block, what's happening there? Our inject method looks like this. Let's break it down. Fundamentally, we are building on top of TracePoint. TracePoint is an amazing piece of technology from the Ruby standard library that allows us to not just see what's going on, but to inject callbacks into execution events. Well, there's no way for me to check the time, but I'll just talk faster as I go. I don't know where I'm at, but we'll see. So we're going to create a trace point here for the event that we're interested in. In this case, we said before call, so we're interested in call events. What we do inside of here is we derive a key for this particular execution event. And we check, does this key match the key that we were initially provided? These keys are those strings. Let's look at this method to derive a key. This is a bit of convenience to make it easier for us in our test to describe the particular execution event that we want to have glitch. And so when we have a call or return event, we can use this string format where we just take the calling object, the object that's being called. We use a dot for class level methods, and we use a pound for instance level methods, and then we just use the method name. So this is a very like human readable way for us to identify a particular execution event. And whenever they match, we're going to continue. If they don't match, we just escape and move on. The next thing we do is we allow you to define matchers, right? So maybe you call one method multiple times with different arguments inside of your job, and you want to glitch a particular one. So you want to match your arguments. This is what deriving matchers looks like. We're in a call in this case. So we see we're just going to take our trace, we're going to look at its parameters, and we're going to use the binding to get the value. Just pass that back. So now we can do checks. We're going to use triple equals here, so you can check like whenever I call it with a string as opposed to an integer, or you can provide it like a concrete specific value. Whenever I call the method with this particular string foo, then glitch, like whatever you need. If you have pass matchers and they match, then we continue. Otherwise, we halt. And at the very end, we just execute the block. What does it mean to execute the block? Well, this is our same basic signal catch, right? We want to run your glitch once, but never again. So we want to have this state to know, have I executed or not? If I have executed, immediately return. Otherwise, we'll flip the switch and we will call the block. All we do now is we enable the trace and run your code. So this is what it looks like to inject a glitch. It's just a layer of convenience on top of TracePoint. But what it does for us here is that it allows us to define a glitch that's going to raise an error, and we can inject that glitch whenever we perform our jobs. So now we have a declarative way to inject side effects into our existing Ruby programs without having to modify those programs. We can just modify them as they run. This is super helpful. This allows us to define failure scenarios. But let's be honest, it kind of sucks. It's like a lot of boilerplate. You want to set up that your job retries on a particular type of error, do the perform later, set up your glitch in all the right way, make sure you inject it. So let's clean that up and provide a much simpler helper. You can just say, run a scenario, right? I want to run a failure scenario. Here's my job instance. You initialize your job with whatever arguments your job needs, and then just tell me how do you want it to glitch. Just provide us with a glitch, use our helpers, glitch before call, job do more things. This is going to make sure that your job retries on the particular error that chaotic job uses, a retriable error. It's going to make sure that everything is wired up, that it will call, perform all jobs, like do everything that you need. This is very declarative, much nicer. But the interesting thing that I realized after I made this helper was if I have tools to declaratively inject failure scenarios into jobs, I wonder if I could simulate all possible failure scenarios for a job. Yeah, I can. So the next helper that chaotic job provides is a testing macro. So you don't call this inside of your test method. This is its own class method that will create dynamically its own test methods. It's going to create a different test for every possible failure scenario in your job. What does that look like? What does that mean? Let's go back to our job here. In this case, here are all of the failure scenarios. We could have a failure occur before our first line ever executes. So we get into the perform method, but we haven't done anything. Somebody unplugs the computer. We could have a failure right after do something is performed, but before do something else. Right after do something else. Right after do more things. All of these are possible failure points. We don't have to specify all of them. We can just say, break this job every single way. And then make sure that these assertions for what it means for this job to be idempotent and correct are always true. Right? These are our invariants. So what this helper now gives us the power to do is to really gain confidence that our jobs are resilient. And we don't have to think, oh, I hope I have thought about all the ways it can break. Like the computer will just break it all the different ways. And the way it does that is it just watches your job once. Let's just run the job once without glitching or anything. And we'll just use tracepoint this time not to inject behavior, but just to observe behavior, just to trace. So I can capture the call stack of your job, paying attention not to all the different dependencies that are being run for each line of code. I just want to see what's happening inside of your job. And I'll capture all of those events. We're not going to walk through all of the code. You can just sort of get a feel for it. The key point here is that the system in the gem can run your job once, capture all of the events in that job, and create a failure scenario for each one of them. And this is how programmatically and deterministically, but exhaustively, we can torture our jobs and then make sure that they match a set of invariants. The nice thing about this particular helper I have found is that using it has taught me how to write assertions that are true invariants. Because oftentimes if I pick a particular failure scenario and I write my assertions, I'm like, perfect, good. And then I switch over and I turn to my test simulation helper and I bring back those same invariants. One of the scenarios breaks an invariant. For me, oftentimes it's the before return. Everything completes, but we don't quite get to return. The job retries and we do everything again. So we run every single operation in our job twice before the job completes. Often in that case, I misunderstood an invariant and it's not quite right. And so just trying to create these types of tests has taught me a ton about how to write good assertions. Like, what does it mean for a job to be idempotent? What are the things I can look at that are invariably true regardless of how many times the job runs each operation, regardless of where exactly the failure happens? So it's also just like a great tool to become better at writing assertions. Excellent helper. Now, the last and most recent feature was I realized after I did all of this, all the trace point orchestration that I had, I was like, hey, what is a race condition, really? A race condition really is a particular linear sequence of operation events. When I merged the operation of two things happening concurrently, where that particular order I didn't expect, and it produces a side effect that I didn't want. I wonder if I could test that. Right? So if we imagine two jobs, do something else, do final thing, do first thing, do another thing, do last thing, and we want to test race condition between these two jobs, we could imagine tracing both of them, right? Getting the full set of their operations, and let's just zip them up, right? Let's just go do something from job one, do the first thing from job two, do something else from job one, do another thing from job two, do the final thing from job one, do the last thing from job two. This might be a particular schedule of interleaved operations. And I can test this exact schedule. Whoop, 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 whoop. Buttons. By just saying, run this particular race. Here are my two job instances, and here's the particular schedule. And I can use the same trace point orchestration to ensure that that exact sequence of execution events occurs in that exact linear sequence, and then I can write my assertions, which is helpful. But once again, as I get back, come on, little guy. But once again, is perhaps overly focused, right? Because you have to pick a particular schedule of operation events. And it has to be in a particular format, which we'll talk about. What would be nicer is, once again, to just simulate. Have the computer find a bunch of race conditions, a schedule of operation events, and just run a sampling of them. Right? Because it's likely going to be a very, very large number, and we won't run all of them, but we can run a sample, and that can be useful. So if we take our same jobs, we could imagine this as a schedule, or this even, or even this. Like, these are all valid schedules. The thing that makes a valid schedule is that you need to have an ordered and exhaustive set of events. Right? So the first operation in job one must always come before the second operation in job one. Right? You got to keep the ordering for each individual job, and you do need to be exhaustive. So every single operation in job one needs to occur, every single operation in job two needs to occur. But if these two things are true, every single way in which you could arrange those two sequences, those two arrays of jobs, is a valid possible race condition. And we can use a similar top-level macro, test races in this case, just give it two job instances, and it can do much the same thing, right? Just run each job once, tracing all of the operation events, take those two arrays, and then do some Ruby permutation math to just say, like, what are all of the possible permutations? Now, again, that number is likely to be huge, so we're not going to run all of them. So by default, test races is just going to randomly sample 200, but random in a deterministic way. So it's going to take your seed, your mini test seed, your RSpec seed, whatever, the seed for this particular test run, and use that to drive the random sampling. So if you run these tests again with the same seed, you will get the exact same sample. Super useful. So random but deterministic, right? We always want our tests to be deterministic. And now we are able to really do a wide array of testing on our background jobs to make sure that they are truly resilient in a number of different scenarios. So to recap, you have some small handful of helpers available to you from Chaotic Job that make it declarative and easy to actually correctly test the resiliency of background jobs. You're going to get running in waves, you're going to get correct ordering, you can inject glitches to simulate particular failure scenarios, you can test a job across all failure scenarios, you can take two jobs and simulate and test a particular race condition or a sampling of all possible race conditions. There are other things that Chaotic Job provides. We have a journal. So if you need to just create a job and do something right? Just to write something that you can read later in your assertions, which is something I do all the time in some of my other gems that work with jobs. You also have a switch. Again, these things are useful when you're writing jobs in your tests in order to test, which you typically do if you're working on some utility or gem that enhances jobs. You can use these tools as well. And that is what chaotic job is. If you happen to have interest in writing more resilient jobs, I haven't talked about it, and I won't talk about it, but all of this work comes out of the work I have done on another gem, an older gem called acidic job. This is a durable execution engine for active job. And as such, I needed to write a lot of tests to make sure that this engine performed correctly under a number of different scenarios. And after writing many, many tests that were very, very ugly, I slowly and surely made those tests good until chaotic job came to life. And I extracted it out of the test suite of acidic job and made it its own gem. But this is a wonderful tool if you have jobs that need to do this kind of orchestration, right? You have a long-running operation with multiple steps spread across multiple jobs. You want to make sure that those jobs are durable and resumable and observable and traceable and orchestratable. Acidic job might be there for you. But that's it for me. Thank you. Feel free to come say hi and ciao.